Hello, I'm Hilary Nye from Google Research and the Google Speech team. In this video, I will be presenting our paper, Audio-AdapterFusion, which is a task ID-free approach for efficient and non-destructive multitask speech recognition. I just want to give a shout out to our authors. So, of course, myself, Rohan, Navraj, Ronnie, Parisa, and Pedro. We are all part of Google Research and as well as the Google Speech team. So I just want to give a quick introduction and background. So to understand our research, you must first understand what residual adapters are. So residual adapters are parameter-efficient, composable alternatives to full fine-tuning of pre-trained models. Generally, in adapter training, we freeze the base model such that we can reuse the base model and train only a few additional parameters on a new task. Adapters have been shown to achieve similar performance as full model fine-tuning, despite only training a tiny number of parameters relative to the full model. In short, adapters are parameter efficient. Because they are parameter efficient, it makes it super useful to solve large ASR models to many tasks. So what does the architecture look like? Well, adapter layers are appended to each transformer base layer. They can be any transformer base layer. And it was actually originally introduced in language modeling for BERT base layers. So in our case, we're using conformer encoder layers. It's a very common speech transformer based model. So there are many different types of adapter positions, but in this presentation, we will mainly be focusing on block parallel adapters. So to explain the difference between block sequential and block parallel, just quickly, block sequential adapters are where the adapter layer is appended after the conformer encoder layer, as you can see on the diagram to the left. And if we look at the diagram on the right, block parallel adapters are where the adapter layer is parallel with the conformer encoder layer. There are also feed-forward sequential and feed-forward parallel adapters, but that's not super relevant to this presentation. So let's dig into the actual architecture of the adapters. So each residual adapter block starts with layer normalization applied to the inputs, followed by a feed-forward layer with down projection to the bottleneck dimension. We can call this bottleneck dimension D. And then it goes through a nonlinear activation function. In the original paper, it was the ReLU activation function. And then another feed-forward layer with up projection to the original input dimension. So how I like to think of it is sort of like a VAE. You're encoding to a smaller latent space and then decoding back to the original dimension. And it essentially, in my mind, how I think of it is it encodes to latent space that represents the downstream task, encapsulates useful information for that downstream task, and then up projects back to the original dimension. So, and then we want to also talk about that the adapter module actually has a skip connection internally, as you can see on the diagram to the right. And the bottleneck dimension enables controls of the number of parameters of each residual adapter module, and therefore the capacity available during adaptation. So essentially, the bottleneck dimension is something that you can tune. And there's a trade-off between number of parameters trained / added parameters to your model, as well as performance. As you can imagine, with more parameters trained, the better the performance. So let's talk about the training procedure. So once the residual adapters are added to the base model, we can train this model by first freezing all of the weights in the base model. Our base model, aka the conformer RNNT, is already trained on large amounts of closed captioning audio, some manually labeled and some pseudo-labeled by a teacher model. And then with only the adapter weights unfrozen, we train this model on a downstream task. So the obvious benefit of using adapters is how parameter efficient this method is when training and serving many downstream tasks, especially when you scale. You only really have one base model and n task adapters, which has significantly less parameters than n base models, because these base models are generally very large. In our case, it's around 120 million parameters. For reference, adapters for a single task with a 512 bottleneck dimension is 7 million parameters. So that's around 5.8% of the full model parameters. Okay, so let's talk about the motivation for this work. In a production setting, a task ID is typically prepended to the input during inference to route to only adapters trained on that specific task. So let's go through this example diagram that we have here. We we tell the model that we are on task A, and so the model runs inference, but only goes through task A adapters and completely ignores task B adapters or any other tasks. So some of the major limitations of this approach are that the task ID needs to be known and set during inference time, which is not always the case that the task ID is known. So another limitation is that this approach restricts the knowledge sharing between adapters trained on different tasks, therefore impeding the model's potential for enhancing generalizability. So the third major limitation is that setting a task ID is very error prone. Setting the wrong task ID during inference could lead to the wrong task adapter being used. If the base model is trained on a different client ID, appending a different client ID to the inputs could lead to degradations in word array since it hasn't seen this client ID embedding before. Thus, using a task ID is not practical for most multitask settings. So let's talk about the main contributions. So we propose 3 novel task ID methods to combine single task adapters to solve multiple ASR tasks. We have adapter mean, adapter weighted mean, and Audio-AdapterFusion. So this work was inspired by AdapterFusion, which was originally introduced in the language modeling space. But unlike AdapterFusion, our methods combine block parallel adapters at each conformer encoder layer rather than BERT layer. And also, the original paper used sequential adapters as well. And then we also add a layer norm before the residual layer. And we empirically show that adding the layer norm before the residual layer improves training stability. To the best of our knowledge, Audio-AdapterFusion or AdapterFusion has not been researched or experimented in the speech space. We also explore 2 different learning algorithms to train our adapter aggregation methods, without or with updating and sharing the pre-trained adapter weights in the knowledge composition stage. So to the left, we prohibit adapter weight mixing, and how to do this is essentially freezing each adapter while we're doing downstream training or training on all of the test sets, all of the different tasks. And on our right, we call this multitask adapters, which is the MTA version. And essentially, it is the same thing, except we unfreeze the adapters and allow them to mix their weights. We also evaluate our methods on 10 test sets from a set of 4 diverse ASR tasks: closed captioning, short-form telephony, long-form telephony, and speech search. So just to give context on the data, closed captioning consists of subtitles or closed captioning data from an online video sharing platform. Telephony short consists of short-form audio collected from call centers. Telephony long consists of long-form audio collected from call centers. And agent-only telephony consists of agent-only long-form audio from a contact center. And speech search is self-explanatory. And we show that our best performing methods are non-destructive. They outperform full fine-tuning on multiple tasks and are on par with the Oracle, aka task ID routing. Non-destructive just means that we avoid catastrophic interference. And we also show that our best performing methods are parameter efficient. They're on par with the Oracle while only updating a tiny fraction of the number of full model parameters. So let's go into our methods section. Okay, let's talk about our learning algorithm. So first, it's the knowledge extraction phase, where we freeze the pre-trained base. Okay, let's talk about our learning algorithm. So first, it's the knowledge extraction phase, which is the same procedure as training residual adapters. So first, we freeze the pre-trained base model, and then we add n task-specific adapters at each conformer encoder layer, where n is the total number of tasks. And then we train each set of adapters on their respective tasks with RNNT loss. So again, to be clear, each set of adapters is trained on their own tasks, and they do not mix data, nor do they mix weights. And then the second step of our learning algorithm is the knowledge composition stage. In this stage, we combine task-specific knowledge to solve multiple ASR tasks. We can visualize adapters trained on different tasks by displaying them as different colors. So as you can see in these diagrams, we have blue, yellow, and orange, all symbolizing different tasks that the adapters are trained on. In the knowledge composition stage, we first freeze the base model. Then we update the adapter aggregation weights, if any. For example, if we use the adapter mean method, we don't add any additional parameters. If it is the multitask adapter version, we will also update and share the pre-trained adapter weights. So as you can see on the diagram on the right, the adapters are unfrozen. Note that the non-MCA version does not mix the weights of adapters trained on different tasks. So moving on to the adapter aggregation methods. As I mentioned earlier, we propose 3 adapter aggregation methods: the adapter mean, adapter weighted mean, and Audio-AdapterFusion. Each adapter aggregation method is shown in the diagram in green, which is where they are placed, which is right after the outputs of the adapters. For the adapter mean, it's relatively simple. We take the element-wise mean of the adapter outputs, and then we take the layer norm of that. And this is interesting in the sense that it requires no additional parameters. And this happens at every conformer encoder layer L. The input of the adapter is also the input of the conformer encoder, as these are parallel adapters. This is the adapter weighted mean, which is very similar to the previous method, except it's the element-wise weighted mean of adapter outputs, and then we also take the layer norm. The green blocks symbolize the added parameters, and they're also the trainable parameters. This requires only L times N additional parameters, where L is the number of conformer encoder layers, and then N is the number of task adapters at each conformer encoder layer. This means that each adapter has a scalar value rather than a matrix associated with it. The scalar value being the weight. So W1, W2, Wn, all the way to Wn for N task adapters. Okay, and then moving on to Audio-AdapterFusion. So in summary, it's the layer norm of the attention on different values of the hidden dimension of each time step of the adapter outputs. At each conformer encoder layer and time step, Audio-AdapterFusion combines useful information from each task to solve a particular utterance. So at each conformer encoder layer, fusion parameters are added to combine parallel adapters for all N tasks. It uses an attention-like mechanism over the adapter outputs. The query is the projected adapter inputs, but it's also the projected input of the conformer encoder layer, since we're using parallel adapters. And the key and value are calculated as the projected stacked outputs of N task-specific adapters. So to explain this in further detail, for each time step T and projection dimension D, we get the probability distribution over the task-specific adapters and matrix multiply it with a value projection. The probability distribution of the task-specific adapters is calculated as follows. For each task adapter, take the matrix multiplication of the query and the key belonging to the adapter and stack these values along a new dimension. Then take the softmax along the new dimension, i.e. the adapter dimension, so that we can get a probability distribution over the task-specific adapters for each time step and projection dimension. And then for each time step and projection dimension, take the dot product of the attention probabilities with the value, and then project the matrix back to the adapter hidden dimension, and then take the layer norm of value and add it back to the conformer encoder layer via a residual layer. An easier way to think of this is our query is the input of the adapters. So given the input of the adapters, that's what we're asking. What combination of adapters information should we use to help predict the downstream task? Yeah, so that's the easier way to think of it. And it differs from AdapterFusion because it combines block parallel adapters instead of block sequential adapters at each conformer encoder layer instead of BERT encoder layer. And then we also add layer norm before the residual layer, as shown in the figure to the right. It's shown in the purple. And we empirically find that layer norm before the residual layer improves training stability and performance of AdapterFusion. So we have some results to show that in the following slides. So moving on to our experiments, we explore our various adapter aggregation methods trained with or without MTA learning to explore, firstly, the trade-off between the number of trained parameters in the knowledge composition stage versus ASR performance. In other words, the parameter efficiency of our proposed methods. And then secondly, we want to see how training with MTA learning affects this trade-off. To investigate our model's abilities to overcome catastrophic interference, we compare our methods to the entire model fine-tuned on multiple tasks, which we call full fine-tuning or full FT, and an Oracle task ID. We define the Oracle as single task adapters trained separately on multiple tasks and evaluated only on their own tasks. The Oracle is equivalent to using a task ID during inference time to route to adapters trained only on the specified task. So we initialize each model with a CC-based model, closed captioning-based model. For the architecture, we have a SunV5, a streaming RNNT, which is with 120 million parameters. We use conformer encoder and a V2 embedding decoder with HAT, and it's trained with FastEmit. As for training data, it's trained on 17.5 hours of CC data, which is pseudo-labeled by a 600 million parameter CTC teacher model. As for the knowledge extraction experimental setup, every adapter has a 512 bottleneck dimension. In the knowledge extraction stage, adapters are randomly initialized to near zero. In the knowledge composition stage, we use pre-trained single task adapters, which were learned from the knowledge extraction stage. And then weighted average weights are initialized to 1 to weight each adapter output equally. So it's essentially initialized to an element-wise mean. And Audio-AdapterFusion weights are initialized with the Xavier initialization, and it also has 512 query key value projection dimensions. We empirically find that a query key and value projection dimension of 512 yields the best word error rate of 256, 128, 64, and 32 for both Audio-AdapterFusion with and without training in an MTA setting. So this is our experimental setup. I won't go into much detail again. I'll let you read the slide. As for tasks and datasets, we have closed captioning, short form telephony, long form telephony, and speech search. Everything is English collected from the US, and utterance lengths are defined as follows. Short form is less than 2 seconds, short form is 2 to 6 seconds, and long form is 14 to 39 seconds. All the data is labeled by either a teacher model or humans. So pseudo labels are provided by 600 million parameter teacher model. It's a non-streaming conformer encoder with chunk-wise attention. It is trained with CTC loss and decoding, and is trained on English closed captioning data. And we diversify our training data via multi-style training, random downsampling from 16 kilohertz to 8 kilohertz, and spec-og. We evaluate our models on 10 diverse test sets from 4 different tasks that vary in sampling rates, utterance lengths, and number of speakers. So this is our train set distribution, and this is our test set distribution. Okay. Moving on to results, let's talk about overcoming catastrophic interference. As shown in the following table, it is clear that full fine-tuning suffers from catastrophic interference when compared to the Oracle task ID. Since full fine-tuning on all tasks, as opposed to using a task ID to route to a set of task-specific adapters per utterance, leads to worse performance on almost all test sets. Specifically, there is a 9.4% increase in mean word error rate when full fine-tuning on all tasks compared to using task ID routing. Just to be clear, full fine-tuning is on the left column, and the task ID is on the right column. As we can see, there's a significant increase in mean word error rate using full fine-tuning. On the other hand, our methods Audio-AdapterFusion, MTA average, MTA weighted average, and MTA Audio-AdapterFusion achieve 8% improvement relative to full fine-tuning and less than 1% mean word error rate relative to Oracle task ID. So as we can see in the table, our methods are on par with task ID and do not suffer from catastrophic interference as much as full fine-tuning. Average performs poorly, worse than full fine-tuning, and weighted average outperforms full fine-tuning and yields a less than 6% mean word error rate relative to Oracle Task ID. Why this is interesting is because weighted average only trains 36 parameters as opposed to 120 million parameters for full fine-tuning, and it also yields better performance than full fine-tuning. So to understand how our proposed methods generalize to new tasks, we perform zero-shot experiments on the speech search test set. As shown in the following table, Audio-AdapterFusion, MTA average, MTA weighted average, and MTA Audio-AdapterFusion outperform the base model in full fine-tuning. MTA weighted average yields the best zero-shot performance with a 9% word error rate improvement relative to full fine-tuning. So let's talk about the parameter efficiency of our methods. Of our best performing methods, MTA average and MTA weighted average are the most parameter efficient. These methods achieve within 1% mean word error rate relative to the task ID, while updating only 17% of the full model parameters in the knowledge composition stage. In the figure shown on the screen, those two methods are circled in red. So MTA average is the orange pentagon, and the blue star is MTA weighted average. So, however, in this scenario where pre-trained task adapters are supplied from different vendors that prohibit the mixing of weights with other vendors or tasks, Audio-AdapterFusion is a good alternative, since Audio-AdapterFusion freezes the adapter parameters and only trains the fusion parameters. Audio-AdapterFusion is seen in green in the diagram. Audio-AdapterFusion achieves slightly better word error rate performance than MTA average and MTA weighted average, but updates 23% of the full model parameters in the knowledge composition stage. Surprisingly, weighted average performs well despite only training a mere 36 additional parameters in the knowledge composition stage, while only training around 0% of the full model parameters in the knowledge composition stage. Weighted average achieves within 6% mean word error rate relative to the task ID. This method allows for extremely efficient knowledge composition and is suitable when there is limited storage space. So in the figure, I circled weighted average in red, and you can see it uses approximately 0% of the full model parameters. So we also perform some layer norm ablations. Layer norm, we empirically show that layer norm significantly improves performance and training stability of Audio-AdapterFusion and MTA Audio-AdapterFusion. To be specific, we yield a 4.3% and a 3.3% improvement in relative mean word error rate when layer norm is added before the residual layer to Audio-AdapterFusion and MTA Audio-AdapterFusion respectively. So in the figure below, we can see that the red and the orange lines are without layer norm, and then the blue and the green are with layer norm. And as you can see, it improves training stability. It doesn't diverge. Also, in general, we yield a better mean word error rate. To be clear, the y-axis is the mean word error rate and the x-axis is the checkpoint. So in conclusion, we present 3 novel methods to combine single task adapters paired with different learning algorithms to solve multiple ASR tasks. We also evaluate our methods on 10 test sets from a set of 4 diverse ASR tasks. We show that our best performing methods are both parameter efficient and are on par with task ID adapter routing, while only updating 17% of the model parameters during knowledge composition. Our best methods can achieve an 8% mean word error rate improvement relative to full fine-tuning and are also on par with task ID adapter routing. Finally, we provide diverse combinations of adapter aggregation methods and learning algorithms to cater to different requirements and limitations of AI practitioners. So for our future work, we plan to explore single task adapters trained on multiple languages to evaluate our proposed method for multilingual ASR, including language mixing. Language mixing is when you use more than one language in a single utterance. For example, if you live in Canada, you might speak a combination of both French and English. Or if you speak Chinese at home with your parents, you might use a combination of Chinese and English. We also plan to improve on domains where data mixing and or weight mixing is prohibited by training single task adapters on such domains. For example, for speech search, which is to search using voice commands, or improving alphanumeric test sets by training on alphanumeric data. So yep, thank you for listening to our presentation, and I hope you build upon this work. Thank you.